Okay, I just want to start off by going over a couple of things that we've covered already, and those are the forces. So we had four main forces that we've talked about thus far. We'll have a force of gravity, Fg. We know we can calculate that using the formula, the force of gravity is equal to mg. We also have a spring force equation using Hooke's law. Force of the spring is equal to negative k times delta x. We have friction, and there's two flavors of it. So static friction, F sub s, is less than or equal to mu sub s times our normal force N, and our other friction force, F sub k, for kinetic friction is equal to mu sub k times N, where N, again, is our normal force vector. Now, we did a couple of problems, some examples using these equations to try to come up with a spring constant or a stretch distance or a coefficient of friction of some kind, things like that. And you saw that in the first worksheet. However, today we're going to start putting things together in a more methodical way. And to do that, we need to talk about Newton's three laws of motion. The first law of motion is Newton's, well, first law, but it says that the sum of forces, and we use the Greek letter sigma, it's a capital sigma, sum of forces is equal to 0. So this is Newton's law of inertia. It says that if there is no net force acting, then there is no acceleration, there is no change in the motion. If something's at rest, it stays at rest. If something's moving with a constant velocity, it continues to move with a constant velocity. Again, that is if our forces are equal to each other, or what we call balanced. So this notation, sigma F, says add all the forces together. We can also call this F net for the net force, or the overall force. If we do a vector addition of all of our forces together, what we get is this sigma F, or F net. And Newton's first law says that that should be equal to 0 if we don't have any acceleration. So maybe I'd think to myself, I could look at a free body diagram. So here's my dot for my mass. Remember, we compress all the mass to the center of mass, and we represent that as a dot. I will have a normal force pointed directly upwards, maybe a gravity force pointed directly downwards, and notice how these are the same length, so they're equal and opposite. But let's say that I had a friction force in this direction, F sub k, so it's moving, there's a kinetic friction, or sliding at least. And then in the opposite direction with the same length, I have maybe a push force, F push. Let's give it a coordinate system as well. So here's our plus x direction, and our positive y direction will be up. Now you might be able to think those friction forces, or that friction force, looks a lot like that push force in terms of its length, but it's opposite in direction. And so maybe if I add those two vectors together, like tip to tail method, we'll see overall 0. And that would be true. So what we can do is we can write for our x direction stuff. I'll write that here for x direction. The forces acting in our x direction are going to be our push force. And notice how it's a vector, so I'm going to put the vector bar on top. So push force plus our friction force. And there's no negative signs here, nothing like that, because all those negative signs are hidden inside of this thing being a vector. So friction is a vector, F push is a vector, and so the negative sign, that's the direction part of our vector, and the magnitude is the number. So if I had like a friction force of 20 newtons pointed in the negative direction, I would call that minus 20 newtons is my F sub k vector, but the magnitude is 20 and the direction is negative. Here we can see that our push force is pointed opposite the direction of positive x, and so it will be negative. I'll write that as minus F push, plus our friction force, F sub k, which is pointed in the positive direction, so it stays positive. Now, I no longer have the bar on top of my force, on top of my vector, because now it is, I no longer have the bar on top of my forces because they are no longer vectors. I've pulled the negative sign out of my F push, that gives me my direction, and then the F push without the bar is just the magnitude. So if I had a 30 Newton push force, it would be 30 newtons for F push, and then the direction is negative x. So these should be equal to 0. And what I can do then is I can add a push force to both sides, F push, both sides of my equal sign. And what I get is that my friction force, F sub k, is equal to my push force, F push. And that's a lot of what Newton's law tells us, is that we can relate these two forces together. We can do something similar in the y direction as well. So here it is. And in the y direction, we have a normal vector plus a gravity vector. And that will also be equal to 0 because we don't expect our object, if it's at rest on top of a table, to accelerate downwards into the table spontaneously or to just randomly start accelerating upwards, right? That doesn't happen. And so our normal force must be equal to our force of gravity for that to occur, at least for this scenario. So our vector normal force is pointed in the positive direction, so I'll call that positive n. And then my gravity vector, that's pointed in the negative direction, so I'll give it the notation negative Fg, and that's still equal to 0. So it tells us our normal force minus our force of gravity is equal to 0. And then if I add a force of gravity to both sides of my equal sign, I will get my normal force equal to my force of gravity, which is just mg from our equation that I wrote earlier. So now we have an expression for normal force. It says normal force is equal to mass times gravity, and that makes sense for a horizontal surface. But why would we do that if we don't really, there's no motion in the y direction? Why would we need this? Well, it's because we have a friction force here on our x direction. That friction force is equal to mu sub k times our normal force, and it's also equal to our push force. So ultimately, we want to calculate what this push force is. And now I have this relationship that I can use to calculate my push force, saying that mu sub k times n is equal to that push force. But we know what mu sub k is, or maybe it's given to us. And so I can write my push force, F push, is equal to mu sub k times m times g. Now, if I know my friction force, or if I know my coefficient of friction and my mass of the object that's interacting with the surface, I will be able to calculate my push force. Again, considering that this would have to be a constant velocity case. So constant velocity or 0 acceleration. And this is a lot of what we do with Newton's first law, is that we set these things equal to each other, we use it to solve for something else. This is a lot like when we would use, say, a distance. We knew how far a ball fell in the kinematics equation section. We knew how far that ball fell. We used that to find out time. Then we took that time over to the x direction, and we used that to calculate maybe a distance if we knew our initial x velocity or something. Here, what we're doing is we're using our y direction to calculate what the normal force is, or to come up with an expression for the normal force. In this case, it's n is equal to mg. And then we use that to plug into our kinetic friction equation to find out the push force, ultimately. So if I knew what mu k and m and g were, well, I know what g is, but if I knew what mk or mu k and m were, I could easily calculate my push force here. Now, some examples, let's say that we have, let's say we have a mu k value given to us. So mu sub k is equal to, well, let's say 0.1. Again, there's no units on this, and it's positive because it's just a scalar mu. It's, there's no vector quality to it, so it can't be negative. We know what g is. That's going to be 10. Let's say that my push force, or excuse me, let's say okay, let's say that we had okay, so let's say that we have a mu k value given to us as 0.4. Again, there's no negative sign, no units on a mu k value because the coefficient of friction, these are scalar quantities, so they can't be negative, and they also just do not have units because they need to work with the other units to give us a force. Usually they work with m and g, and so that would be mass is in kilograms, g is an acceleration, meters per second squared. A kilogram times a meter over second squared is a Newton, and so if mu k has any value or any units, it won't work out for us to be a force. Anyways, we'll say mu k is 0.4. We'll say our mass is 25 kilograms, and we know what G is. So I can calculate my push force, F push, as, from the previous page, as being mu k times mg. Plugging that into my calculator, plugging that in, gives me 0.4 for mu k, 25 kilograms for m, and 10 meters per second squared for g. Again, this is not negative 10 meters per second squared because g is not a vector here. G is the scalar version, and it just has that 10 meters per second squared as its magnitude, and no positives, no negatives for direction. So again, it's just mu k times n times g, where g is positive 10 meters per second squared. If I plug that into a calculator, I should get around 100 newtons is my push force. And this is really important that we understand this is a zero acceleration picture. For us to use Newton's second law, for us to use Newton's first law, we have to have zero acceleration / constant velocity type of situation. But this is just the magnitude of my push vector. If you recall, I had a direction. So here's my positive x, here's my positive y's up, and my push force was actually in the negative direction. So I'm going to have to do some thinking to get my push force as a vector instead of just a scalar. As we have it written here, it's just a scalar with the magnitude of 100 newtons. But my F push vector is negative 100 newtons in the x direction. So negative 100 newtons in the x direction. That's what the little x with the little triangle thing above it is called. Those are called hats, by the way. The x little thing above it is called a hat, and it indicates that this is a unit vector pointed in the x direction with a magnitude of 1. So that is all for our Newton's first law. It's pretty straightforward, but it's actually just a special case of Newton's second law, and I'll get to that in another video.